Okay, hi and welcome to video notes 9.3 on multiplying binomials. We've done this before. We've done with the distributive property. I don't know if we've done with binomials though, so that might be new for us if you've been in my class. But what I'm going to start with is a new method. You don't have to use it, but it's really good for organization. And you'll see at the bottom when the polynomials get larger, it's kind of useful actually, because drawing the little arrows for distributive property can be a bit of a problem sometimes with that. But if we're asked to multiply two binomials, and let's just recall what a binomial is. So a binomial is two monomials added or subtracted together, something like this, 2x plus 4. So if we're asked to multiply that binomial to a different binomial, say 3x minus 7, which we're going to do frequently, especially when we introduce polynomials and specifically quadratics, because they make a quadratic usually. When we're asked to do that, this box is kind of helpful. So let's take a peek at what it looks like. You're going to go ahead and make a box, make a cross in the little box so it has 4 sections to it. When you do that, each of the columns and rows will be designated to one of the terms from the binomials or one of the monomials. So you can see 3x is here, and then there's negative 7. I'll switch back to a green color here. There's 2x there, and then there's the 4. Again, the multiplication for that's going to be when they combine. So in this box here, we're going to take that 2x, right, and we're going to multiply it by 3x, which is 6x squared. In this corner of the box, we're going to go ahead and take 4 and multiply it by 3x. That's going to be 12x. Again, 2x to this box is going to be intersecting with this negative 7. So 2x and negative 7 are going to make negative 14x. Again, be very cautious to take your negatives with you. That will cause you to have mistakes if you don't. And then finally, 4 times 7. You can kind of see how that works, right? Wherever they intersect, rows and columns, you multiply those numbers. Here's another example. Make sure that you pause and do it. But let's go ahead and start with one of these. You can write it on this side or this side, the bottom or the top. But as long as you've got one along the top and one along the side, you're good. Doesn't matter which way they go? No, not at all. So I'm going to go ahead and take the first one, write x here. I'm going to write 3 here. Probably going to put positives in front of them so that I remember that they're both positive. And I'm going to do the same thing for the x plus 6. So positive x and positive 6. Now I'm just going to go ahead and start my multiplication. For some reason, I generally start where my x's intersect because I kind of like to see the x squared. So in this case, x times x is x squared. My next combination really doesn't matter where I go, but let's take 3 times x or 3x. Now I'm going to take 3 times 6 or 18. And then finally, I'm going to take x times 6 or 6x. One thing to note from this is that these sections, if you kind of multiply it that way, if you have your x's first, will always be like terms and that you'll combine them. It's kind of nice. So I know that I'm going to add those two together because they're like monomials or terms. So I'm going to end up with my highest degree to the left, x squared, right? Because we're going to write this in standard form, of course. We don't want to ever forget that, standard form. And then I'm going to go ahead and put my linear term, because this is my quadratic term, put my linear term next. So 3x plus 6x is 9x. And then finally, I'm going to put my 18, which is my lowest degree of 0, technically correct. And that's going to finish it off. Now, the multiplication that we're used to doing this with is the distributive property. And really, that's all we're doing. The boxes are just a different way to look at the distributive property. I'm not going to spend a ton of time with these. We can do one really quickly, but I will say this. Distributive property and FOIL are really the same thing. I don't like the acronym FOIL because it confuses you. You have to remember a process. With the distributive property, guess what? It'll work for any polynomials that you multiply together, be it a 3-term, 4-term, 5-term, or a 100-term. It doesn't matter. You can multiply as many terms and the distributive property will work, and as will the boxes. Okay, but FOIL will only specifically work for binomial times binomial, and it's kind of a naming feature than it is an actual math feature. But just to remind you what the distributive property looks like, you're going to take each piece of the polynomial, or binomial in this case, and multiply it to each part of the other binomial. So I'm going to start with 2p squared times 2p. Just to review, if we haven't done that yet, remember that your coefficients multiply, so I'm going to get 4 there, and my exponents add of like variables, of course. So 2 plus 1 is p cubed. Then I'm going to take that 2p squared and I'm going to multiply it by negative 5. So I'm going to get negative 10p squared because there's no p's on that 5. Then I'm going to start my other distributive property for my other monomial term. So I'm going to take 3 and multiply it by 2p. So I'm going to get positive 6p. And then I'm going to take 3 times negative 5 or negative 15. Now when you do the distributive property, oops, I think I squared that. Oh, I did square that p. 6p squared. So in this one, when we're done, I forgot that this is the way that this one worked out. Notice we're not going to get like terms here because that first term was squared. So I've got a cube term, a quadratic term, a linear term, and a constant term. And we're done with this one. Okay, so where are you going to see this distributive property of binomials? Where are you going to see this box multiplication? Here's a kind of a simplistic form of it, but it's something that you could use in your daily life. Make sure that you pause and look at one here. But the gist of this problem is that we're going to have some area that we want to find with a cutout in the middle. So we want to find all of this shaded region here, and we want to know this area. Sometimes it's a walkway, sometimes it's a patio, sometimes it's grass for landscaping, but whatever it happens to be, we want to know that area. Maybe the inside's a pool, maybe it's a deck, maybe it's a house, whatever it is. But to get that, we know that, and here's the best part about this, we can find area by multiplying two sides of any rectangle. So if I take this side here, 5x plus 8, and I multiply it by 6x plus 2, then I can find the area of that large rectangle. Similarly, if I take and multiply these two sides, I get this small rectangle on the inside, and if I subtract them, I'm left with just that shaded region. And that's our goal with this. So to get the area of the shaded rectangle, the larger one, I'm going to take one of the sides, so 5x plus 8, and I'm going to multiply that by its other side right here, which is 6x plus 2. Due to space, I'm going to use the distributive property versus the box there, just because I don't have a lot of room. So my first multiplication is going to be 5x times 6x. Remember, coefficients multiply, so 30, and exponents of the variable that are alike add, so 30x squared. Then I'm going to take 5x, I'm going to multiply it by 2, so I'm going to get 10 and just an x. Then I'm going to take 8 and I'm going to multiply it by 6, and I'm going to go ahead and get 48 on that and an x. And then finally I'm going to take 8 and multiply it by 2, and I'm going to get 16. My like terms are going to show up here in the middle. Those are my like terms, so I'm going to add those there. So I'm going to end up with, for this one, 30x squared plus 58x plus 16. That represents the area of the shaded. Again, we'd have to know what x is to find a number, but we're ready to calculate it if that scenario comes up. So the area of the unshaded here, we're going to find that. And you'll notice that the unshaded rectangle, which is down here in the center, has one side that's a monomial, so 5x, and it has one side that's x plus 6. So we're going to write that down. Again, we'll distribute here. I'm going to go underneath because I'm running out of room. So 5x times x is 5x squared. And then again, 5x times 6 is going to be 30x. Now, there's not too much to do with that one because there's no like terms, nothing that can be combined. But if I take those and I plug this into this little formula that I just said here, the area of the shaded minus the area of the unshaded, I'm going to get the area of the overall region that we're looking for that's unshaded, or that is shaded. So I'm going to take that and plug that in here. I'm going to take this one and plug it in here, which I've done. You can see how that plays out. Now, one thing not to forget, remember with multiplication, this is the trickiest part about multiplication. Subtraction of two polynomials. I was saying multiplication there. Is that this negative do not ignore it. It has to be distributive. You have to distribute that negative to every term that's in the parentheses of the polynomial that's being subtracted. Have to. Okay, so you can see that I've distributed that negative to both. What does that mean? It just means that the signs switch. So if this is a positive 5x squared, it becomes a negative 5x squared. And if this is a positive 30x, it becomes a negative 30x. Like terms are in the yellow. You can see I've combined those. Like terms are in the green. You can see I've combined those, and then 16 plays out. So from there, then, we're going to go down to our last example. And this happens to be not binomial multiplication. This is a trinomial times a binomial, where a trinomial times a binomial doesn't really matter how it plays out. But the great thing about the box when you do this, if I have all these arrows here, it's difficult to keep track of them because they start to be too many. So a lot of times what I'll do, and you'll notice how messy that is. See how messy that is? I won't use my distributive property method. I'll actually just draw a box. There's a couple reasons. As you can see over here in this one, my like terms will always be on a diagonal. So I already know what's going to be combined up. So when I move from the box, I can go right to the final polynomial after it multiplies out. But remember with these boxes, you have to change the box shape based off the number of terms. So this one has a trinomial, so I need 3 columns. You could go tall. I usually go wide, but it doesn't matter. So let's go ahead and put our x here and our -3 here. We're going to do this example. And I'm going to put 2x squared here, a negative 3x squared, or a negative 3x there. I don't want to forget my signs, so I know what they are. And then my last piece then is a positive 1. Again, wherever they intersect, that's the multiplication that comes out of it. So I'm going to start here at the top. X times 2x squared is going to give me 2x cubed. Negative 3 times 2x squared is going to give me negative 6x. X times negative 3x is going to give me negative 3x squared. Negative 3 times negative 3x is where they intersect here. I'm going to get a positive x because those two negatives turn into a positive. X times 1 is just x, and negative 3 times 1 is just negative 3. So I'm going to go ahead and highlight. Here are my like terms here. And I'll switch colors and highlight again. Here are my other like terms here. So when I combine these to write the final result, I'm going to get my largest term, put it in standard form. It's a cube. That's my largest monomial in that set. So I'm going to write 2x cubed. Then I'm going to combine these, which is going to give me a negative 6x squared and a negative 3x squared. So I'm just going to combine the coefficients. Two negatives make a more negative value. So I'm going to get negative 9x squared. 9 and a 1x is going to give me a 10x and a negative 3. And that's going to be the polynomial that comes from the trinomial being multiplied by that binomial. So just to recall, you've learned how to use the box to multiply larger polynomials. You've also seen where the application of this is. So you're going to see it in some type of a area minus an area to get a shaded a region. You'll see that in some of the examples and homework that you've done. You've re-seen the distributive property, and you've also seen how to use the box for multiplication. Good job. See you in class.